Hello, in this lesson we're going to be looking at continuity and differentiability and trying to determine whether a function is differentiable at a given point. So let's review our three-part definition of continuity. How do we determine if a function f of x is continuous at a point where x equals a? Well, first of all, we need to have f of a defined, or we can say f of a exists. That has to be true. So you should start by finding f of a. Write down what f of a is equal to. If it doesn't exist, we can immediately stop and say the function is not continuous at x equals a. Next, we need to have the limit as x approaches a of f of x be defined, or I could say exists. So you could say f of a is defined, or f of a exists, the limit exists, or the limit is defined. Either one is fine. And then the third thing that we need to happen is that the limit of f of x as x approaches a has to equal f of a. Because if the first two things are true, but the last statement is not, then that means we have a removable discontinuity. We have a hole in the graph, and the graph is not continuous at that point. So we need all three of these statements to be true in order to conclude that f is continuous at the point where x equals a. Now, what does it mean for a function to be differentiable at a point x equals a? So we've sort of defined differentiable loosely as the derivative exists. So here we can just say, well, we've got some nice abbreviated notation that we can use. It means that f prime exists at x equals a. So f prime of a exists. That's what it means when we say f is differentiable at x equals a. It means that f prime of a exists. So the slope of f at the point where x equals a exists. In other words, that slope is not undefined. Let's look at a more formal definition of differentiability. A function f is differentiable at x equals a if f prime of a exists, and that means that the limit as h approaches 0 of f of a plus h minus f of a over h exists, because that is our limit definition of derivative. Or we could say a function is differentiable at x equals a if the limit of f prime as x approaches a from the left is equal to the limit of f prime as x approaches a from the right is equal to some finite value, which here we're just calling L. So L has to be a real number. If L is infinite, if it's infinity or negative infinity, then that's not going to work, and our function is not differentiable at this point. So in order for f prime of a to exist, f of a must exist, because we're using f of a in the definition of f prime of a, right? If f of a doesn't exist, then immediately we can conclude that f prime of a does not exist. If f of a doesn't exist, let's just say there's a hole in the graph where x equals a, we can't say that the graph has a slope at that point because there's not even a point there, right? So f of a has to exist in order for f prime of a to exist. A good way to think about differentiable functions is that they're locally linear. And what do we mean by locally linear? So hopefully you know what it means to say something is linear, right? If it's linear, then the graph looks like a line. So locally linear means maybe it's not linear when you zoom out and look at the big wide picture, but if you were to zoom in really, really, really close on that point where x equals a, it's going to appear linear. So locally means, well, just think about the word local, nearby, right? And when we're saying locally here, we mean really, really, really nearby. Really, really close as you can imagine getting to the point where x equals a without actually being at the point where x equals a. So in the graph here, we have a quadratic function. Right here, starting with the quadratic function. All of these graphs are just zoomed in versions of the same function. And if we were to zoom in on this point right here and make it a little larger, we would get something that looks like this, right? Here's our x equals 1. And if we zoom in on that, and blow it up a little bit, we'd have something that looks like this. And then if we zoom in on that and zoom in on that and keep zooming in, if we zoom in really close, we see that at this point, it doesn't really look like a parabola anymore. If I showed you a graph that looked like this and asked you what kind of a function is it, you're probably going to say it's a linear function, right? It looks pretty linear. The closer we, and if we could keep doing this, just zoom in on that little piece and blow that up, it's going to look linear. And what line is it going to look like? Well, it's going to look like the tangent line at that point. It'll be indistinguishable from the tangent line at that point. That's what we mean by locally linear. If we zoom in close enough, the graph is going to appear to be linear. It's going to behave as though it were linear. Let's look at a few different examples. So here we have the graph of, and we're given the equation, f of x equals the absolute value of x plus 2. So it's just the parent absolute value function shifted up 2. Is this function defined at x equals 0? Well, when x equals 0, we can see that there is a point on the graph, 0, 2. So yes, it is defined at x equals 0. I could also say f of 0 exists, or f of 0 is defined, or just f of 0 equals 2. So yes, it is defined at x equals 0. Is f continuous at x equals 0? Yes, it is. We can see that on the graph it's continuous. There is not a discontinuity at x equals 0. The graph is continuous there. We could run through the three-part definition, but I think intuitively, if you can just look at the graph and see that it's continuous, that's fine. But if we were using the three-part definition, we would say, does f of 0 exist? Yes, it does. It's equal to 2. What is the limit of f as we approach 0 from the left? It's 2. What is the limit as we approach from the right? It's 2. All three of those things were equal to 2. Therefore, the graph is continuous at that point. Okay, now how about the limit of f prime of x? So remember that f prime of x is referring to the slope, not the actual graph we're looking at, but the slope. What is the slope of the graph as x gets close to 0 from the left-hand side? So what is the slope of the graph as we approach x equals 0? Well, the slope is -1. And what is the slope as we approach 0 from the right-hand side? So we come in this way. What is the slope approaching? Well, it's just always equal to 1. Those are not the same value. The slope as we approach 0 from the left is -1, but the slope as we approach 0 from the right of f is +1. So this limit of f prime of x does not exist as x approaches 0. Okay, so that's a problem. Limit of f prime of x as x approaches 0 does not exist. Is f locally linear at x equals 0? It is not. So let me clear some of this away. If we were to zoom in on the graph right here, what would it look like? It would still look like a V. And if I were to zoom in on that point and blow that up, what would it look like? It would still look like a V, right? No matter how close you zoom in on that, it's never going to look linear. It's always going to look like it has a V shape to it. It has a corner point. We call that a corner point, like a sharp turning point. So no, it's not locally linear. Is it differentiable? No. So we can cite a couple of different reasons here. First of all, going back to our definition, if this limit is not finite, then f is not differentiable at the point you're approaching in the limit. Okay, so that is one reason we could give. Or this is another reason, it's not locally linear. So in order to be differentiable, a function has to be locally linear. That gives us a really easy way to just look at a graph and see if it's differentiable or not. If you can imagine, is it locally linear? Because it's very easy to look at this graph and see it's not locally linear at that point. That's probably an easier way to think about it than trying to figure out what is the slope approaching from the left-hand side and what is the slope approaching from the right-hand side. So not differentiable, and that's true at any kind of corner point. This is an example of a corner point. A function f is not differentiable at a corner point. Okay, this next example, is the function defined when x equals 0? Yes, it is. Again, we have f of 0 equals 2. Yes, f of 0 equals 2. Is f continuous at x equals 0? Yes, it is. We can see that from looking at the graph. There's no discontinuity at x equals 0. what is the slope of f as we approach x, as x approaches 0 from the left. So what is the slope? For slope, you have to imagine the tangent lines. In the last example, those tangent lines were all just y equals -1 or y equals +1. But here, those tangent lines are changing. And if we were to zoom in really close on this point right here, just exaggerate it a little bit more, what are the slopes doing? So they're getting steeper and steeper as I get down towards that. This time it's not called a corner point, this time it's called a cusp. So the difference between a corner point and a cusp is that with a cusp, your slope is approaching infinity or negative infinity on either side. So in other words, your tangent lines are approaching a vertical line. Whereas on a corner point, that's not the case. You just have two different slopes on either side of your point. But here, the tangent lines are getting more and more vertical. So the slope is approaching, it's too hard to draw the tangent lines. It's just going to look like I'm drawing a bunch of lines on top of each other, right? But they're like kind of getting more and more like this. So they're approaching, but they were negative. These were negative slopes. Decreasing lines have negative slopes. So negative infinity from that side. And then over on this side, they're positive slopes, and they're getting steeper and steeper and steeper as I come in closer towards that point. So we're approaching positive infinity on that side. Okay, so right away from that information right there, I can conclude no, not differentiable at x equals 0. F is not differentiable at x equals 0. But I could also conclude that by just looking at the graph and observing that it's not locally linear at this point, right? If you zoom in really close, that is not going to appear linear. It's still going to look like a cusp. So not differentiable. Wrong one. Not differentiable because it's not locally linear. Here is the function defined at x equals 0. Yes, there is a point there. F of 0 equals 2. Okay, so that's not an issue. Is f continuous at x equals 0? Yes, it's continuous at x equals 0. There's no discontinuity at x equals 0. What is the limit of f prime as x approaches 0 from the left? Well, our tangent lines, right, coming in here, they are becoming more and more vertical. They're positive slopes, but they're getting steeper and steeper and steeper and steeper. So infinity. As we approach from the right, okay, these slopes, these are also positive slopes, and they're getting steeper and steeper and steeper and becoming vertical. So also infinity on that side as well. Is f locally, but right here I can just stop and say, nope, not differentiable, right? The limit of f prime has to exist in order for it to be differentiable. Is it locally linear? Well, is it locally linear? So this one is kind of interesting to think about. If you zoom in super close on that point, is it going to look like a line? Yes, it will. But what kind of line is it going to look like? It's going to look like a vertical line. And a vertical line is not a function. So is it locally linear? Well, I mean, it's approaching a line, but not a function. It's approaching vertical line. So we're going to say no, but for a different reason. It's because it has a vertical tangent. This graph has a vertical tangent. If you were to draw the tangent line at x equals 0, it would be vertical. And so in that case, we say that our function is not differentiable at that point. And then in this fourth example, is the function defined at x equals 2? Yes, we have a point here at 2, 0. F of 2 equals 0, so yes. Is it continuous at x equals 2? It is not. It is not. So I've circled the point on the graph here. It is not continuous because there's no left-hand limit as x approaches 2. We've got nothing to the left of 2. Okay, so we would not say continuous at x equals 2. No. And if it's not continuous, then immediately, no, not differentiable. Okay, that's a deal breaker. Discontinuity is a deal breaker. A corner point is a deal breaker. A cusp is a deal breaker. A vertical tangent is a deal breaker. Immediately, when you see any of those things, you know your function is not differentiable at that point. What is the limit of f prime as we approach 2 from the left? Well, you can't approach 2 from the left because there is nothing to the left of 2. There is no point directly to the left of x equals 2. So it doesn't exist. Not even possible to try and approach from the left. 2 from the right would be infinite, and these are positive slopes, so we're approaching from the right. So infinity. Locally linear? No, because no matter how close we zoom in on that graph, we're not going to see a linear looking function. We're going to see something that has a distinct endpoint and then just stops. So not locally linear. So lots of reasons where we could stop and say deal breaker, right? There, there, and there. Okay, so to summarize, a function f is not differentiable at x equals a if x equals a is any of the following: a corner point, a cusp, a point of vertical tangency, or a point of discontinuity. Those are all things that would make f not differentiable. So one of the things on this list is a discontinuity. If f has a discontinuity, immediately it's not differentiable at the place where there's a discontinuity. So it must be true then that f is continuous in order for it to be differentiable, because if it's not continuous, it's immediately not differentiable. The only way it can be differentiable is if it's not continuous. Does not have a discontinuity, right? The only way it can be differentiable is if it is continuous, So let's consider this example. There's lots of interesting points on this graph, and we're just going to look at all of the even positive integers that are listed here. So 0, 2, 4, well, not 0. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and 22. And at each of the points on the graph with that x-coordinate, I want you to think, is the graph continuous and differentiable at that point? Is it continuous but not differentiable at that point? Is it differentiable but not continuous? Or is it neither continuous nor differentiable? So underneath the point, maybe you can just like write A if you think it's A, or B if you think it's B, and so on. So pause the video here and take a moment, go through each one of those points. At each one of those x values, I want you to determine if the graph is continuous and if it's differentiable, right? What combination of those two things are we seeing on the graph? All right, let's start with x equals 2. So here's the point in question where x equals 2. The graph is continuous. We can see by looking we don't have a discontinuity. It is continuous. Is it differentiable? Well, at x equals 2, there's not a corner point, there's not a cusp, there's not a discontinuity, there's not a vertical tangent. It's a nice, smooth graph passing through that point. So it is continuous and it is differentiable. A. When x equals 4, okay, we're at this point right here, but let me erase that so we can actually see what's happening there. Is it continuous? Yes, we do not have a discontinuity at that point. It's continuous. It's continuous, so it's either going to be A or B. Now, is it differentiable or not? Well, we have a corner point here. Corner points don't have to be linear like we saw with the absolute value. You just have to have a different slope as you're approaching the value x equals 4 from the left than you do when you approach from the right. So if I were to cover up the left side of this graph, just hide it so you couldn't see what was happening on the other side of x equals 4, and you had to approximate, draw a tangent line here. So imagine this point right here, draw yourself a tangent line and estimate your slope. We would say it's what, maybe like positive 1.5-ish. So m equals 1.5 as we're approaching 4, x equals 4 from the left-hand side. Okay, let's do the same thing if I cover up the left-hand side and hide that so you can't see what's happening on the graph over there. If we just cover that up and I say, what do you think the slope is? Like draw yourself a point right there, draw a tangent line. What do you think the slope is going to be? Well, it looks like the slope is approaching 0, right? That not the positive 1.5 that we saw on the other side. So two different slopes based on whether we're approaching 4 from the left or the right. And so we call that, when that happens, we call that a corner point. Okay, this is an example of a corner point. It's not as obvious as the absolute value graph's vertex, but this is still a corner point, so not differentiable. It's continuous, but not differentiable. At x equals 6, we have a removable discontinuity. That's immediately a deal breaker, not differentiable. And it's a discontinuity, so not continuous. So that is a neither continuous nor differentiable. All right, so here we have, well, draw the arrow right there, removable discontinuity. At x equals 8, we have corner point, deal breaker. So it's continuous, right? We don't have a discontinuity. It's continuous, but it's not differentiable. At x equals 10, it's continuous, right? There is no discontinuity there. It's continuous, but right at that point right there, vertical tangent. Those are hard to spot sometimes on the graph if you're thinking about it too quickly. Vertical tangent, so that's a deal breaker. It's continuous, but it's not differentiable. X equals 12. What do we got going on here at x equals 12? At x equals 12, we have a jump discontinuity. Discontinuity is a deal breaker. And a discontinuity literally means not continuous. So it's not continuous and it's not differentiable. D. X equals 14. Nothing interesting happening there at all. It's nice and smooth, continuous. So continuous and differentiable. X equals 16. Again, nothing alarming happening there, no discontinuity. There's no corner point, no cusp, no vertical tangent. What did I leave out? Or no discontinuity, yeah. So it is, we're good to go. It's continuous and it's differentiable. 18, we have a discontinuity deal breaker. It's a discontinuity, so not continuous, and then immediately not differentiable. It's neither. All right, that's a jump. Discontinuity. Okay, 20. 20. Is it continuous? No, this one is an, I don't know where to put the arrow, infinite discontinuity. We've talked about 4 different types of discontinuity, right? A removable discontinuity, a jump discontinuity, an infinite discontinuity, and an oscillating discontinuity. So vertical asymptote represents an infinite discontinuity. If it's discontinuous, then immediately, if it's not continuous, immediately it's not differentiable. So that's a D. And then 22. 22 is a nice happy part of the graph. It's smooth, continuous, differentiable. It's all good. A. So looking at our answer choices, what is the one that we did not use ever? The one that we never used. And that doesn't mean that necessarily that we couldn't. Maybe I just didn't put an example like that on the graph. But I think that question is going to come up. Differentiable but not continuous. We never use that. Is it possible for a graph to be differentiable but not continuous? Well, remember, not continuous means discontinuity, and discontinuity is immediately a deal breaker for differentiability. So not possible. It is not possible for a function to be differentiable but not continuous. That is not possible. Differentiable but not continuous is not possible. That is an impossible scenario. Okay, recap. In order for a function to be differentiable, what 2 things must be true? First, number 1, it must be continuous, and let's be specific. In order for a function f of x, let's be really clear. I should have been more clear there. For a function f of x to be differentiable at x equals a, what must be true? F must be continuous at x equals a. If it's not continuous, you can immediately conclude that it's not differentiable. So in order for it to be continuous, what must be true? F of a exists. The limit of f of x as x approaches a must exist. I can just say exists. And those two things must equal each other. The limit as x approaches a of f of x must equal f of a, otherwise we could have a removable discontinuity. And then number 2 has to do with the slope, the f prime of x. The limit of f prime of x as x approaches a has to exist. So that means you can't have a different slope as you approach a from the left than you do as you approach a from the right, because in that case the limit of the slope would not exist. Okay, so let's try some examples here. Consider the function g of x. This is a piecewise function. On the subdomain from 0 to 3, g of x equals the square root of x plus 1. On the subdomain from 3 to 5, not including 3, g of x equals 5 minus x. Is g of x continuous at x equals 3? So of course they're asking us at x equals 3, which is right where the domain splits, right? So in order for g to be continuous at 3, we have to make sure that the limit as we approach 3 from the left is equal to the limit as we approach 3 from the right is equal to f of 3, well, g of 3 in this case, not f. Okay, so we'll start with g of, it's a hard habit to break, g of 3. What is g of 3? So we look at the subdomain that includes 3 right here. That's the first subdomain. So g of 3 equals the square root of 3 plus 1 equals 2. Okay, so we've got that. Now we need the limit of g as x approaches 3 to also be 2. So let's check that. The limit of g of x as x approaches 3 from the left, we have to go from the left and the right because 3 is right where that domain splits. From the left equals the square root of 3 plus 1 equals 2, so that's good. So far, so good. And then the limit of g of x as x approaches 3 from the right is going to equal 5 minus 3 equals 2. Excellent. That all 3 are the same value. So we can say yes, it is continuous. G is continuous. So therefore, G is continuous at x equals 3. Please do not forget to do this part. A lot of times on the test, I'll see students find the left-hand limit, find the right-hand limit, and then just immediately conclude that it's continuous. You have to also write down that you found g of 3. If you don't check that part, there could be a removable discontinuity, and any kind of discontinuity means not continuous, so you must check that part as well. It's called the 3-part definition of continuity for a reason. There are 3 things to check. Okay, number 2, is g differentiable at x equals 3? Now, in order to figure out if g is differentiable at x equals 3, we are going to want to find the limit of g prime of x as x approaches 3. And because 3 is where the domain splits, we're going to have to find the limit from the left and the limit from the right. All right, so this is somewhat difficult to do for us at this point because we don't have an equation for g prime of x. Now you know what you need to know in order to find the equation for g prime of x. It's going to take a little bit of effort. Let me erase and make some room. In Unit 3, we're going to start to learn some very quick ways to find derivative equations without having to use the limit definition where h approaches 0. But for now, we're sort of stuck with having to do it the long way. So I'm just going to start working in this empty space over here. I want to find g prime of x, and that's the limit as h approaches 0 of g of x plus h minus g of x over h. which is the limit as h approaches 0 of the square root of x plus h plus 1 minus the square root of x plus 1. Right? G of x plus h means you replace this x with an x plus h. G of x means you replace this x with an x, which isn't going to do anything. Okay. All over h. Now, I really didn't give myself any space because I have to multiply the numerator and denominator by the conjugate of the numerator. So let me move this down here so I have more space. I'm going to multiply by square root x plus h plus 1 plus square root x plus 1 over, same thing, and I'm going to then distribute or FOIL out the numerator. So I get x plus h plus 1 minus x plus 1 over, and I'm not going to simplify the denominator because I'm hoping that I can eventually cancel out an h from the numerator and the denominator. So in the numerator, that's going to simplify nicely. We've got x minus x, and we've got 1 minus 1. So all that's left in the numerator is h, and that h is going to cancel with that h. So limit as h approaches 0 of 1 over the square root of x plus h plus 1 plus the square root of x plus 1. Now we substitute 0 in for h equals 1 over the square root of x plus h plus the square root of, no, sorry, we're letting h equal 0. So we're going to get 1 over the square root of x plus 1 plus the square root of x plus 1. So 2 times the square root of x plus 1. Okay, that is g prime of x for that first subdomain. So I'm going to erase this work so I have some space again to write my g prime of x equation. 1 over 2 square root x plus 1 from 0 to 3. Now the next one is going to be a lot easier to figure out because it's a linear function, and we know how to find the slope of a linear function just by looking at the equation. It's -1. So -1 on the interval from 3 to 5. Okay, so now the limit of g prime I can find using this equation for g prime. The left-hand limit, we're going to use the top piece, and that's going to be 1 over 2 times the square root of 3 plus 1 equals 1/4. The right-hand limit, we're going to use the bottom piece, -1. Those two numbers are not equal to each other. 1/4 does not equal -1. Okay, so no, not differentiable. Yes, we saw that it was continuous. No, it is not differentiable at x equals 3. Not differentiable. For what values of k and m will the function below be both continuous and differentiable at x equals 3? Okay, so we know what we need in order for it to be continuous. We need h of 3 to equal the limit of h as x approaches 3. And in order for it to be differentiable, we need the limit of h prime of x to exist as x approaches 3. So let's first just worry about continuity. So continuous. What has to be true in order for it to be continuous? Well, let's find h of 3. H of 3 is, so here's where x equals 3. H of 3 equals k times the square root of 3 plus 1, or 2k. Then we need the limit of h as x approaches 3 to exist, but 3 is right where the domain splits, so we have to find the left-hand limit separately from the right-hand limit. So the left-hand limit is using the top piece, so that is also k times the square root of 3 plus 1, or 2k. And then limit as x approaches 3 from the right of h of x, and that's using the bottom piece, so m times 3, or 3m, plus 2. Make sure you don't skip this step here. Continuity has a 3-part definition. If you skip finding h of 3, you could have a removable discontinuity, so you have to show that you're checking for that. Okay, so in order for this to be continuous, 3m plus 2 must equal 2k. Now that's not enough information for us to solve for m and k just yet, so let's move on to differentiability. For differentiability, wow, that's a long word, and I probably wanted to say differentiable anyway. Differentiable. In order to make sure it's differentiable, we need the limit of h prime of x as x approaches 3 to exist. Now to find the limit, and again, 3 is where the domain splits, so we're going to have to do this separately. We're going to need a left-hand limit and a right-hand limit. To find this limit, we're going to need an equation for h prime of x. What does h prime of x equal? Well, we saw in the last example how we can find the derivative of k times the square root of x plus 1. It's a long process. Once we start Unit 3, we're going to start learning easier ways to find a derivative that don't require us to use the limit definition. And so I'm just going to go ahead and tell you what that is, because this is one that I can do in my head, and you will learn how to do it in your head as well. The derivative of k times the square root of x plus 1 is k over 2 times the square root of x plus 1 on that same interval, so from 0 to 3. And then the derivative of mx plus 2, you should be able to do that one in your head because that's a linear function, and you know that the slope of a linear function is just the m that we're seeing as the coefficient of the x. So 3 less than x less than or equal to 5. Now I can find the limit of h prime as I approach 3 from the left. It's going to equal k over 2 times the square root of 3 plus 1, so k over 4. And the limit of h prime as I approach 3 from the right, there is no x to substitute the 3 in for, so it's just m. Okay, so the only way this is going to be differentiable is if k over 4 is equal to m. Otherwise, that limit's not going to exist. So now I have a system of equations that I can solve, and I'm going to solve this system of equations using substitution. I know that m equals k over 4, so I'm going to substitute that in for the m over here. So 3 times k over 4 plus 2 equals 2 times k. Let's multiply both sides by 4. We get 3k plus 8 equals 8k. Subtract 3k, we get 8 equals 5k. So k equals 8 over 5, or 16 over 10, which would be 1.6. And then to solve for m, we know that m equals k divided by 4. So 8 over 5 dividing by 4 is the same as multiplying by 1/4. And that's going to be 2/5. Okay, so k equals 8 over 5 and m equals 2 over 5. Last example, for what values of a and b will the function below be differentiable at x equals 1? So this doesn't say continuous and differentiable, but remember, if a function is differentiable, it's automatically continuous. So that's still going to be true. It's really finding what values of a and b are going to make the function f continuous and differentiable. When you see differentiable, it's implied that it will also be continuous, because it cannot be differentiable without being continuous. So it's not always going to say continuous, but you can assume as soon as you see a function is differentiable, you can assume that it's also continuous. All right, so we're going to do the same thing that we did in the last example. For continuous, we need to make sure that f of 1 equals the limit of f as x approaches 1. So f of 1, 1 is included in this top subdomain, equals 3a times 1 squared plus 2b times 1 plus 1. And then the limit of f as x approaches 1 from the left is going to be the same thing, 3a plus 2b plus 1. The limit of f as x approaches 1 from the right is going to be a times 1 to the power 4 minus 4b times 1 squared minus 3 times 1. So the left-hand limit here must equal the right-hand limit. 3a plus 2b plus 1 must equal a minus 4b minus 3. Let's group our like terms. So if I subtract a on both sides and add 4b to both sides, and then subtract 1 on both sides, I get that. If I divide everything by 2, then I have an equation that relates a and b. So we're going to hold on to that and move on to differentiability. For differentiability, we're going to need to find the limit of f prime of x. So let's find f prime of x. I don't know if I have enough room to write it on the side, so let me write it right here below. F prime of x. Okay, again, just to save us a lot of writing to figure this out the long way, I'm going to tell you what the derivative of f is. This is one that I can do in my head, and once we get into Unit 3, you will learn how to do this in your head as well. So f prime of x for that top piece is going to be 6ax plus 2b. And for the bottom piece, it's going to be 4ax cubed minus 8bx minus 3. All right, so for differentiability, I'm going to put differentiable, we need the limit of f prime as x approaches 1 from the left. So we're going to substitute 1 in for x into the top piece. That's going to be 6a times 1 plus 2b. And then the limit of f prime as x approaches 1 from the right, we're going to use the bottom piece. So 4a times 1 cubed minus 8b times 1 minus 3. Those have to be equal to each other. So 6a plus 2b equals 4a minus 8b minus 3. And then rearranging terms, 2a plus 10b equals negative 3. That's my second equation in my system of equations. Okay, so a plus 3b equals negative 2, and 2a plus 10b equals negative 3. So you can decide if you want to do this using substitution, if you want to do it by elimination. I'm going to do elimination. I'm going to multiply the top equation by negative 2. So negative 2a minus 6b equals positive 4. I multiplied the top equation by negative 2, and then I'm going to add these together. So that cancels out, and I get 4b equals 1, b equals 1/4. b equals 1/4, and now I can use either one of the equations. I'll just come over and use this one right here to solve for a. So a plus 3 times 1/4 equals negative 2. So I'm going to subtract 3/4. A equals negative 2 minus 3/4. So that's 2 is the same as 8/4. So that would be minus 11/4. So a equals negative 11/4 and b equals positive 1/4. And that wraps up our lesson on continuity and differentiability. Next time we are going to look at tangent line approximations. Thanks for joining.